Next we have exercise 10. It's a result, it's actually a theorem that we will prove in this exercise. The steps of the proof are given as parts of the exercise. We have to solve each part and that way we will get the full proof. So let's see what the theorem statement is. There are two well-ordered sets J and C, and there is an assumption on them that there is no function that maps J onto C. Then we have to prove that there exists a unique function h from J to C such that this is true. What is this? You take any element x in the domain J of the function h, then the value of the function h at that element is this. Let us try to understand first what this part is. We already know what Sx means. Sx is the section of J by the element x. So this is the set of those elements of J which are less than x. Now because h is a function from J into C, the h image of the set Sx will be a subset of C, obviously. Because there is no onto function from J to C, in particular h is not onto, and that is why there is no possibility for this image to be equal to the entire set C. That means this h of Sx will be a proper subset of C, and as such, if we consider its complement in C, which is this difference, then that will be a non-empty set, and the complement of course is the subset of C. Now C difference h of Sx is a non-empty subset of C, and C is well ordered, so this non-empty subset will have a smallest element. That is this right hand side. Okay, so we have to prove that a unique such function exists for which this will be the case for every element x in J. That's the claim of this theorem. And this condition, this equation has been given a name also, star. Now let's see what the individual parts are that will ultimately be combined to have a proof of this theorem. Part A actually will finally be used to show that such a function h is unique. What do we have in part A? If we have two functions h and k which map either sections of J to C or all of J into C, and both of them satisfy this star, this condition for all x in their respective domains. They will have, each one will have its own domain. So if this star is satisfied by both of them for all x in their respective domains, then we have to show that h of x is equal to kx, k of x, for all x in both the domains. That means if in the for those x that belong to both the domains, these two will be equal. So let us first solve this part A and then we will see the other parts. Instead of a detailed solution to part A, I have this hint for you. You go back and see the proof of lemma 8.2 and you will get the full idea of a solution to part A from that proof. Okay, I won't say anything more than that. Let us next see part B. This is not a very difficult thing. You just go to the proof of this lemma and you will get the idea quickly. Let's next see part B. So what we did in the solution is, in the beginning itself we straight away defined the function k like this. Because the domain of k should be S alpha union this singleton set alpha, so our input either will be an element in S alpha or will be equal to alpha, and accordingly I have defined K partly like this. If the input A belongs to S alpha, then K of A is H of A. But if the input A is equal to alpha, then this is the definition, which looks exactly like the condition star in the original theorem. Now let us first see if K makes sense, if it is well defined, because otherwise it is not a function. Say this condition is true, that the input belongs to S alpha. Then on that A, I can obviously apply H, because H has S alpha as its domain. And what is then this H of A? It's a unique element of C. So if this is the condition, then K of A is a unique element of C. So this part of the definition is okay. Next, if A is equal to alpha, then this by definition is K of A. What is going on here? We have already seen that condition star, so we at least know what this means. However, how do we know that C difference H of S alpha is a non-empty set? You recall the statement of the original theorem. In that statement, we have the condition in the beginning itself that there is no onto function from J to C, and alpha is some element of J, right? So S alpha is a subset of J. Now, if this H is onto, it won't be onto, but say I am saying that this is onto, then using this onto function, you can extend this to the entire set J to create an onto function from J to C. And it's given that that is not possible, and that is why H, this function itself is not onto. And that is why H of S alpha is a subset of C, but it's not equal to C, it's a proper subset of C. So just like the condition star there in the statement of the theorem, here also this difference is a non-empty subset of C, and because C is well ordered, so there will be a smallest element. So in this part of the definition of K also, K of A is a unique element of C again, and that is why K is well defined. The fact that this K, just like this H, also satisfies the star, it's left to you to show. You may be thinking that I am not doing enough here, but you also need, it's an opportunity for you to think about these things and come up with an argument yourself. At first it will seem very complicated, but you just take one part of your argument, think about it properly, write it down nicely, and then you go to the next part. So that way you will see quite quickly that it's really not that difficult of a task. So you please do this part. You verify that this K also satisfies star. So that means we have part B. Next, part C. Next, this is part C. In part C, we have a subset K of the original set J. And for each element alpha in K, there exists a function H alpha from the section S alpha into C, which satisfies condition star. Then we have to show that there exists a function K from the union of all these sections S alpha into C, which also satisfies star. Let's see the solution. So here also, just like part B, we straight away define the function K like this. X, of course, the input is going to come from this union. K of X is defined to be equal to H alpha of X if X belongs to S alpha. However, you encounter a problem immediately. It won't be a problem, you will see ultimately, but at present it's a problem. it is not given that the sets S alpha are mutually disjoint. So if our input X belongs to more than one S alpha, so which H alpha should we apply on X? In other words, is this K of X really going to be unique? If it is not unique and if it depends on the choice of alpha, then this is not a function, this is a general relation. And the S alphas actually are not disjoint. I mean, if you think of it, you have an alpha, you can think of the well-ordered set J, or actually K, a part of J, as a line. It's after all a linearly ordered set as a line. So you have alpha here and you have beta here. Okay. So S alpha is the set of all elements in J that are less than alpha. So this side. And S beta is the set of all elements of J that are less than beta. So these two sets are not disjoint. That common part is there. So in that case, will K of X be H alpha of X or H beta of X? So we have to first of all clarify this. In other words, we have to show that K is well defined. So let's see how that can be shown. So let us start by supposing that K is not well defined. That means something goes wrong with this definition of K, that it really depends on the choice of this alpha. So that means our supposition will be this. Suppose there exist distinct elements alpha and beta in K such that some input X belongs to S alpha as well as S beta. It belongs to their intersection, but H alpha of X is not equal to H beta of X. So if someone sees that X belongs to S alpha and uses H alpha of X to calculate Kx, and someone else uses S beta, sees that X belongs to S beta and uses H beta of X to calculate Kx, then the two persons are getting two different values of Kx. So that's a problem. We should not have two outputs for a single input. Alright, now can we get a contradiction from this supposition? Let us consider this set. The set of those elements Z in S alpha intersection S beta which are like this X, that is at which H alpha and H beta do not agree, they are different. This is it's of course a subset of the set J. It's non-empty because X belongs to this set because of this condition, because of this supposition. And our J is well ordered, so this non-empty subset will have a smallest element. Let that smallest element be Y. Okay. Since Y is the smallest element of this set of problematic elements Z which create problem for this function, anything less than Y does not belong to this set. So nothing less than Y is problematic, which means that if you consider any element from Sy, from the section Sy of J given by Y, then in this set you precisely have those elements that are less than Y. None of them belongs to this set. That means for all of them, H alpha is equal to H beta. When you evaluate H alpha and H beta at such a point from Sy, they are equal. So obviously the entire image of Sy under H alpha is equal to the image of Sy under H beta. Alright. Now recall that our H alpha satisfies condition star. So by that condition, H alpha of Y is the smallest element of the difference C minus H alpha of Sy. But this is equal to this. So that's what we used here. That, however, in turn is equal to H beta of Y. But now you have got a contradiction, because you see y being the smallest element of this set is after all an element of the set. So h alpha of y should not be equal to h beta of y, but that is what we have got, and this contradiction arises from this supposition. So the supposition must be wrong. That is, even if some x belongs to different sections given by different elements, ultimately it does not matter which section you use to calculate kx, you are going to get the same output, and that is why k is well defined. Let us write that. Okay. Alright, so that's a contradiction. So the last supposition is wrong, and this proves that our function k is well defined. And then you have to verify that star is satisfied by k. So that part is left to you. Let us next see the next part, part D. So in part D, we have to show by transfinite induction that for each beta belonging to J, there exists a function h beta from S beta into C which satisfies star. Transfinite induction is the version of induction that you have on general well-ordered sets. For that you can go back and see exercise 7, I think. Anyway, so let's see the solution now. So in the solution, we start by considering the set of those alphas, those elements in J for which this claim is true. That is, for which there exists a function h alpha from S alpha into C that satisfies star. To apply transfinite induction, we have to take any section S alpha as a subset of J0. If we can then show, that alpha is coming from J obviously, if based on this assumption we can then show that alpha also belongs to J0 as an element, then by the principle of transfinite induction, J0 will be equal to J. So when that happens, then for every alpha in J, this will be true. So our claim will be proved. So now we have to show that alpha belongs to J0. Let's see how. Now actually two cases arise depending on whether the element alpha has or does not have an immediate predecessor. It may not have, but say alpha has an immediate predecessor beta. Then the section S alpha obviously is S beta union this beta, singleton set beta. Now since beta belongs to J naught, where is this coming from? You see, beta after all is an element of S alpha, and this is our hypothesis that S alpha is contained in J naught. So that is why beta belongs to J naught, and that is why by that hypothesis there exists a function h beta from S beta into C satisfying star, because that is the definition of J naught. Then by part B, you go to part B. Part B directly says that in that case there exists a function h alpha from S alpha into C satisfying star. So that way alpha will then belong to J naught. That is if alpha has an immediate predecessor. Next comes the case where it does not have an immediate predecessor. Next we have this case. If alpha has no immediate predecessor, then you can check that S alpha will be the union of all S betas where beta is less than alpha. No such beta is an immediate predecessor, however. Okay. Now there exists a function h beta from S beta into C satisfying star for each beta less than alpha, because we have already made the hypothesis that S alpha is the subset of J naught because of that thing. But then by part C, you go to part C and there in place of K you consider S alpha. By part C there exists this type of function that we are seeking, a function K from S alpha into C which satisfies star. So in that case as well as in this case, alpha belongs to J naught. So on the assumption that S alpha is a subset of J naught, we have proved that alpha belongs to J naught. So by the principle of transfinite induction, J naught is equal to J, and that completes the solution to part D. And finally we have another part, E, where we are to prove the theorem finally. So these are just steps that come before that. Next we have part E. So this is the final part. Here we have to prove the theorem. And here also there are two cases. In the first case, we assume that the set J has a largest element, small j. This may not exist, so there will be another case on that. Then by part D, there exists a function h from Sj into C, which satisfies star. So Sj is the section of j by j, and that is why by part B, there exists a function h from Sj union this singleton set j into C, which also satisfies star. But clearly, since j is the largest element of j, so Sj union this singleton set j is nothing but the entire set j. So that way you will have a function from j into C which satisfies star. So that's the original claim of the theorem. Now let's go to the other case where j has no largest element. So in this next case, our set j has no largest element. Then by now you know very well that j will be equal to the union of all these sections of elements of j, Sx. Then by parts D and C with this time k equal to j, we conclude that there exists a function like this that we are seeking from j into C which satisfies star. So here this thing ends. Ends means we have proved the existence of such a function. But what about its uniqueness? Uniqueness follows from part A, and that completes the proof. So that actually concludes this section entirely. So in the next topology video, we are going to really start actual topology from the definition of topology. So let me end the video here itself, and tomorrow also we have upload. So tomorrow we will see something new. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.